All right, we're going to quickly review a new Obsidian sourcing app that we produced. First, a quick note on file formats. This will allow you to look at spectra, net counts, and then a spreadsheet as well. If you want to import from multiple instruments, because obviously some archaeological products could use more than one XRF instrument, you can do so down here. In any case, in this case, we're going to use a spreadsheet of about 1,000 Obsidian sources gathered from a Mayan site in Belize. So we'll go ahead and upload that. Next, we'll come over to counts, where it'll automatically produce a table of the results using all the elements it identifies. We're going to remove those elements we don't need for Obsidian sourcing and focus on the most reliable ones for geochemical sourcing, which include rubidium, strontium, yttrium, zirconium, and niobium. Now, with those 5 in place, we could also, if we wanted to, add categories. Now, what I mean by that is we can add lat-long information, we can add qualitative information about the sources, or even quantitative. And so this could include stratigraphic information, tool type, etc. So you can isolate out some from the population and look at others. In this case, we're just going to do a quick run, however. I'm going to come over here to model prep. Now, what I mean by model prep here is we need to define the spatial universe that these tools could have come from. If you do a global search for Obsidian, you might get some anomalous results. There might be a source in Japan that by pure coincidence matches one in Mexico. So in this case, we do want to restrict the area that'll be analyzed. You can do this using modern political boundaries. You could also use lat-long. If I choose lat-long, my interface changes to include latitudes and longitudes. I'm going to stick to a political map. Right now it's looking at the USA. It includes the states that have Obsidian, and then it gives me an estimate of the total number of Obsidian sources that we have in our database that have rubidium, strontium, yttrium, zirconium, and niobium in them, which is about 291. Since our site is in Belize, we're going to add some new areas, which include Mexico, Honduras, and Guatemala. Now, when I add that information in, the provinces and basically smaller subsections of that country are included, and I can just remove some if I need to. So I'm going to remove sources in Baja California and then the northern deserts, since that's a bit far out for the Mayans. That brings us down to a respectable 44 sources. I can also change the model sensitivity. Now, what I mean by model sensitivity here is the threshold for which we will process the fingerprinting algorithm. So let's say I have an Obsidian source of about 150 parts per million rubidium, and I have a model sensitivity of 10%. If that's the case, I will process those sources that fall within 15 ppm of that Obsidian source. It's basically the percentage of the total we're going to use. And now, it might seem like with Obsidian, you'd be safe doing a much lower number, such as 5%. Now, that might be true for the region you're looking in, but what I found using the app is that there are 2 complications you need to consider. First, you need to consider the measurement of your analysis technique, whether it's XRF or neutron activation analysis. Second, you want to consider the error that may exist in the published literature. Some sources might have errors in them. Some might have had geochemical concentrations analyzed using faulty premises. In any case, you have a certain expectation of variance of around 10 to 20 parts per million based on the published literature, which really challenges us to try and find that perfect match. The reason we use this database is that we know where these Obsidian samples come from. They're well researched and well understood. So this is used as a test of the app. Now, when I go ahead and go to the results tab, it'll begin processing the data, which is to apply the fingerprinting algorithm over and over again. If I come over here and we take a look at my activity monitor, do you see all those R's right there? That is the app running in the background using multiple cores in my processor. You can see the spike in my CPU load right there. What's happening in this case is that because we're analyzing so many different combinations, I've got 1,000 artifacts, I've got 44 sources, analyzing every combination there, it isn't a question of multiplication. You raise 1,000 to 44. So obviously it's going to take some time to process all that data. By using multiple cores, we can basically string the same operators through multiple processors to speed up the process. So we go from taking 10 minutes to taking about 1 minute to analyze even very large data sets. Now, quick note on that kind of parallelization is right now only available for Mac computers and Linux computers. If you want to use this app with Windows, which you absolutely can, you'll be using serialization instead, which is a little slower, but will still offer speed improvements. In general, the more cores you have on your computer, the faster the app itself is going to run. A quick note on the fingerprinting algorithm that is used in this app. What it is doing is for those sources that match the threshold, it's treating rubidium, strontium, yttrium, and zirconium and niobium as a time series line, and then calculating an R-squared, extrapolating from that a t-value, and then from the t-value doing a scaled z-score test to see if the highest number is significantly different than all the others. A quick note on that approach: if it does not find a match, it won't report a match, which means we will rule out all sources if your sample source is small. When the analysis is done, you'll see a summary table emerge as you see right here. In this case, El Shayel, which is a nearby volcano, is the source for about 891 of these artifacts, or about 83% of the total assemblage. Ishtapeke has 141 artifacts coming from it, or around 13%. And then the rest of the sources appear to be much smaller ones in Mexico, though Sierra de Pachuca, which is in a mountain range near Mexico City, does have a respectable 2% contribution here as well. If I come over to sourced artifacts, it gives the source for each artifact uploaded. So you get more than just the total proportion, but each individual artifact. So you can see here FN 960 with 142.4 parts per million iridium, 140 parts per million strontium, etc., is sourced to El Shayel, whereas FS 93 with only 97 parts per million rubidium is sourced to Ishtapeke. The other great thing about the app is it'll use the lat longs for the sources to produce a source map that'll show you roughly where your sources come from. Now, it auto-produces this map. We can also adjust the map over here by adding lat long coordinates to create a little bit better of a clip, because again, it's just a computer. It won't have the same eye for detail that you will. So I'm going to drop my latitude to 11, and we're going to extend our longitude to -85. And so now we have a map that's a little nicer. And you can see a little more clearly here, El Shayel and Ishtapeke, which are quite close to each other. The site is up here in Belize, so it's not too far away, are proportionally larger than all the other sources included. I can download that map, and it'll automatically produce a map that is in TIFF file format that is ready to be uploaded to a journal of your choice. Publishing research myself, I know how much of a pain it can be to choose the right DPI and resolution. So I coded the app to automatically comply with the majority standard for scientific peer-reviewed journals. Now, that's for the source map. You can also download the data itself. So I'm going to download in Excel format the results of the analysis. We'll throw it over here, and we'll open it up in Excel. So let's close up here, and let's open it up over here. Now, the first thing you'll see here is the same as what you saw in the app itself, which is the ranking of the sources based on the contribution. The new information provided here is it'll provide you with the citations we use to compile the database. So that way everything is transparent and you are able to include that information. Model parameters includes number of samples, the potential sources based on a geographic identity, the total number of identified sources, and then the sensitivity. As we add to the app and choose more options, it'll also change the parameters as well. The source identification, if you don't provide lat long information, is based on a t-value, which is basically an r-squared value corrected by an r-squared value corrected by the sample size or the number of elements chosen. Generally speaking, the higher the t-value, the better. So in this case, for El Shayel, sources that have scored 19 or 40 are going to be quickly attributed to a nearby source. Whereas Ishtapeke, you can see here, 25 beats 2.46. So that source will be identified as Ishtapeke. You can find those results back here of the source. You'll also receive the z-score. This is a scaled z-score. So we scale the t-values to the normal distribution, and then we pick those that have the highest z-score. And then we do a z-score test against that mean to see if that source is significantly a higher match than all the others. And here you can see with very exceptionally low p-values, it's most often the case. Generally speaking, when you see something like this, a Sierra Pachuca has a little bit lower of a p-value, that means that there are other sources close to Sierra de Pachuca. And so we don't have quite the same height of confidence, though in this case, it does a significance test. So you can see here, the p is not less than 0.05 here. So this would be a non-significant match to Sierra de Pachuca. That information is available here. The source match column is used for your own internal testing if you want. Some people like to include some samples of El Shaya and Ixtepeque just to make sure the app is working, and this will just tell you quickly if it matches. To make this work, you have to name the sample the same as the source that is being tested. R value gives you just the raw correlation information, and then finally p-value gives you the p-value match for all the potential sources. And that is provided down here. So in any case, this raw data is available so that if you decide that you don't want to use my automatic source attribution, which is absolutely fine, even encourageable, you can use this raw data to decide your own source assignments as well. Now, we're cognizant that people like to do principal components analysis and other kind of quantitative analysis, so we provide that option here too. So here, the dots are the individual artifacts that are analyzed, and the ellipses represent the sources. So in this case, we use the mean and standard deviation from the published literature to inform the source ellipses. You can remove ellipses for sources that you think might be falsely attributed. So I'll get rid of Osotero, Otumbo, Navaras, Los Humeros, and who else? El Physical. I'm going to remove that one as well. I should note that the app does correctly distinguish between El Physical and El Shayel, which can be difficult given their similar properties. So in any case, this gives you an idea of the variance. So you can see here, Sierra de Pachuca is a pretty good match, El Shayel is a good match, and then Ixtepeque is here too. If you have outliers, you can just float your mouse over them, and it'll give you the sample number and the source identified by the app. Now again, the source identified by the app is provided as a convenience. The data you may want to use is the raw output from the app to help you assess its match to other sources. And of course, you can play around with sensitivity or change your geographic descriptions to eliminate some of these other sources as well. But this gives you a nice PCA table. And as before, you can download that PCA table in a format that is publishable, formatted to be published in a scientific journal. If I come over to elemental ratios, we have the same basic app presented as well. But instead of doing a PCA, this is just the raw data. So if this is the case, I can come in and I can plot, let's say, El Shayel, Ixtepeque, and Sierra de Pachuca, and I think Piedra was another one that looked promising. So these are those plots presented here. As you can see, rubidium versus yttrium, probably not the best way to identify these sources because you can see just how much isospace is taken up with just that source. So what I can do here is I can ratio them. So I'm going to ratio rubidium to zirconium. I think I'll switch this to strontium, and we'll ratio that to zirconium. Now, as you can see here, this produces much tighter clusters. As before, you may find some points fall outside, and you can use that information. You can see these guys here fall completely outside, which might be worth investigating those artifacts individually. As you know, sometimes black chert or other materials could sneak in, or perhaps the obsidian is so thin that we're getting a distorted view of the rubidium or the zirconium, which is not impossible either. But this plot too, you can download and use it as a publishable figure. So all in all, that's a quick overview of the app. You've got multiple options to analyze your data. There is an automatic model, but I would treat the automatic model not necessarily as a true positive, even though for these specific results, we're very confident and they match by and large the source assignments done by archaeologists, but also treat it as a negative test. We have very high confidence that we can rule out sources, and that can be done automatically using this app. If you have any questions, you feel free to email me at lee@pri.services. Again, that's lee@pri.services. And in the meantime, happy sourcing.